Thank you. Hi, everyone. So it's nice to be here for such a big audience. So I'm very happy. So I'm going to talk to you today about System F and specifically System F interacting with less typed languages. We're going to look into two specific cases where we have this phenomenon, and then look at questions related to full abstraction. And so I'm going to tell you a bit more about that. But so first, let's look at System F. So I don't think I have to introduce System F at POPL', right? So that should be fine. What I'm interested in System F is typed reasoning, the typed reasoning that you get in System F. For example, in this example, we have two functions that accept a function f of type for all x, x arrow x. So this is System F with, so I'm thinking about System F with general recursion, right? So this function should in principle be able to do two things, right? It can either return the argument that it gets or it can diverge, right? So that means that these two functions should always behave the same, no matter what way we use them. So they are contextually equivalent. Why is that the case? On the left, we see that f is used at type bool and applied to true. So that should either diverge or it should go into the then branch. On the other side, we apply f to unit, and that should also diverge whenever it diverges on the left, or it should return unit, right? In the second example, we have a similar phenomenon for existential types. We have two values packed as a value of exists x arrow x x. So that should it should be unobservable from the outside whether this existential value contains a unit and a value unit or true. Okay, so this all follows from a property known as parametricity, which again at POPL I don't have to introduce, I hope. So this is the typed reasoning that we're interested in. And now the question is, if we look at System F interacting with less typed languages, with languages where we don't have parametricity as a sort of built-in feature, can we somehow still preserve this typed reasoning? So we're gonna look at this in two specific settings. So the first is a compiler, which is known as the ceiling compiler, which was proposed a long time ago by Sumii and Pierce. Okay, so what is the idea? Let's imagine we compile System F to an untyped lambda calculus. Okay, so and the naive approach is just we erase all the types. And unfortunately, this, so one problem with this is that this breaks equivalences. Particularly the second example where you have an existential package containing unit on the left and true on the right. They should be equivalent. They are equivalent in System F. But if we just erase the types, erase the packing and so on, then we get unit and true in the untyped calculus, which are observably different, right? So two things that are equivalent before compilation become inequivalent after compilation. So this means that our compiler is not what we call fully abstract. Fully abstract is a property. Fully abstract compilation is a property which says essentially that two terms before compilation should be contextually equivalent if and only if their compilations are contextually equivalent. And Abadi, in a very seminal paper in 1999, Abadi proposed that fully abstract compilation should be seen as a kind of formulation of secure compilation. So what does this have to do with security? It's all about seeing the context as a kind of adversary that tries to break properties that hold in your source language by exploiting the additional power that you have in your target language. So I'm not going to go into details about the security aspect of this story. Right, so let's just think about contextual equivalences here. So how can we fix this? This is the idea proposed by Sumii and Pierce a while ago. So we need some kind of primitive in the target language that lets us enforce some kind of abstraction. And the abstraction primitive that they looked at was sealing or seals, which is a kind of primitive that models a kind of ideal encryption, right? An unbreakable encryption. So how does it work? We get a few additional primitives. So we get a way to allocate new seals, and let me just quickly show you how these things behave. So this new x.t, it says that I want to run my term T and get a new fresh seal. So think of a seal as a kind of encryption key. So I'm sort of generating a new encryption key that nobody else is already using. So how does this work? We keep track of a heap H, which is a list of all encryption keys that are already in use. We choose a fresh one. We choose one that's not yet in H, and we run T with X bound to this fresh key sigma. Okay. So what can we do with this seal? We can use that second construct, so with the angle, the accolades or whatever the curly brackets, where we take some term T1 and we seal it with a term T2, where the term has to evaluate to this seal, and that's essentially how we model encryption. So we encrypt term T1 with this T2, which evaluates to a seal sigma. Okay. So then how does decryption work? So if we have the seal and we have something sealed with that seal, we can unseal it, right? So we can decrypt the value that was sealed. So that's this fourth construct. It's a bit more complicated. So how does it work? So we have this term T2, which evaluates to which is supposed to evaluate to a sealed value. We have this term T1, which is supposed to evaluate to a term which evaluates to a seal sigma that we know. If the two seals correspond, then the decryption works. We have the right encryption key. So we run the then branch with the decrypted value bound to X. If it doesn't work, if the seals are different, then we go into an else branch where we can sort of choose what to do next. Okay. So sealing an idealized model of encryption. How can we use this to enforce parametricity when compiling to an untyped calculus? So how does it work? What we're going to do is we're going to first erase, but then apply a wrapper that sort of dynamically enforces the guarantees implied by the type. In this case, for example, this wrapper at type exists XX is just going to allocate a fresh seal and seal the value with that seal, and then throw away the seal, right? So you just take the thing you're looking at, you put it in a box, you lock it, and you throw away the key. Okay, so that is, I think it's intuitively clear that should make the two terms equivalent again, because I mean, you throw away the seal, no one else can ever get access to the seal again, so they can never look inside this encrypted package. Okay, in more interesting examples, we're not always gonna just lock something and throw away the key. Sometimes we're also gonna keep the key and unlock it again when we get it back from the context, right? For example, let's just look at the above example. So we have a package which has an X, but also a function X arrow unit. And what's it gonna do? How is the wrapper gonna work? It allocates a fresh seal. It seals the unit value with this fresh seal, but then in that second function, when you get back a value of type X, you can unseal it with your seal, right? Because this is a trusted code, and we can then use the encrypted value that we just got back from the adversary. Okay, so is this sufficient to enforce full abstraction? So this is the So Sumii and Pierce, in a paper from 2000, they conjectured that it was, right? So that this sealing compiler was sufficient to enforce, to make sure that all the contextual equivalences that you have in system F are preserved after compilation. There's a bunch of related work after that. Some people even, there's even a paper where they say we were trying to prove this full abstraction theorem, didn't work, but we proved this other thing instead. So there's a lot of work related to this. There's also a lot of other work related to this conjecture. So it's attracted quite some attention over the years. Okay, so that's our first problem domain we look at. Another domain where we have an interesting interaction between system F and a weaker type system is gradual typing. There's also a lot of work on building a gradually typed language around system F. So a language where you can mix system F code with untyped code and have them interact properly. Okay, so what is gradual typing? So the general goal is we want to build a language where we can embed typed and untyped code and let them interact nicely. We want to, this is sort of seen as a sort of incremental migration path from untyped code to typed code. So I have a big code base without types. I want it to become typed, so what I'm going to do is I'm going to gradually take every module, add types, type annotations, make it typed, and hopefully in 10 years I'm going to have a nice typed code base. Okay, so what are the formal guarantees that we want if we build a gradual type system? So there's some work on this. There's a lot of people. There's a paper which I forgot to mention here, which proposes a number of correctness criteria, and it expresses all sorts of intuitive properties. Obviously, you want to, when you're embedding a typed language and untyped language, you want this embedding to be correct, right? To preserve the behavior of the terms. You also want that the interaction between the typed and the untyped code is sort of correct, and this is formalized by a theorem known as a gradual guarantee. You also want to, and then finally, and this is something we're interested in, you want to gradually gain the benefits of typing. So if you add type annotations, you don't want to wait until your whole code base is typed to actually get type safety. You want to get this sort of gradually. In the modules where you have already added type annotations, there should be no more type errors, right? Even if it interacts with the untyped code. So one question, and one thing that we think is missing in this list of correctness properties, is some property that expresses another benefit of typing that we would like to preserve, and namely source language reasoning, right? So types are not just useful for type safety. They don't just make sure that we don't use a string where we want an int. Sometimes we also get useful reasoning principles. For example, the reasoning that I showed you in System F. So then the question is this benefit also preserved in our gradually typed language? One way to express this is that we get a fully abstract embedding of the typed language into the gradual language. So what does this mean? Two terms that are contextually equivalent in the typed language should still be contextually equivalent in the gradual language when they are interacting with untyped code. So what does this mean for concrete gradual type systems? Specifically, we're interested in the gradual type system built around System F. So this is known as the polymorphic blame calculus. There's a number of papers about this. There's also a new one which I haven't listed yet at ESOP 2018, which you should all read because it's interesting. So how does this work? They built a blame calculus around System F where they use a notion of runtime type generation to enforce parametricity. Essentially, whenever you get a new abstract type, you don't just use the underlying type, but you build this new fresh runtime type, which is kept distinct from the actual type it's instantiated with. So I'm not going to go into details about this, but it actually works surprisingly much like the ceiling that I showed you, except it's a bit more static than that. Okay. At ICFP 17, Amal Ahmed and others showed that this gives you a form of parametricity in your polymorphic blame calculus. So you get some kind of relational parametricity, so some kind of typed reasoning even when interacting with untyped code. Okay. So you see that this work, these people already do a lot of work to preserve relational reasoning. So I think this strengthens the argument that it might be useful to actually formulate a theorem that expresses that this actually works, that we actually are preserving some kind of typed reasoning. So this, namely the thing I mentioned on the previous slide, this fully abstract embedding of the typed source language. So we preserve some typed reasoning. Do we preserve all equivalences from the typed language? Do we have full abstraction? Do we have this fully abstract embedding in the blame calculus? It turns out that the answer is no, in both cases, both for the ceiling compiler and for this polymorphic blame calculus. So let me try and explain you the problem. This is the counterexample that we built, and it uses this type which we call the univ type. And the univ type is listed there, and it sort of expresses the existence of a universal type. So there exists one type X, such that for all types Y, we can embed values of type y into X and also extract them again, extract values of type X again into type Y. So what you can show in system F is that first, univ is not an empty type. There are plenty of inhabitants. So we're looking at a non-terminating variant of system F. So you can just build a value of type univ where one of the functions diverges, and that works fine, right? So that, I mean, it's not an empty type. But what you can show in system F is that univ only contains what we call degenerate values, right? In the sense that if you take this single type X, you take some value of some type, you embed it into X, and you get it out again, that must diverge. You can show this using formulations of parametricity from the literature, right? So univ only contains degenerate values. Unfortunately, in both of our cases, in both of our applications, that is not the case in our target language. So under the ceiling compiler, before I go into that, let me first show you that you can express that the fact that univ contains only degenerate values. You can sort of exploit this to obtain a contextual equivalence between two terms. So how does this work? We build two functions that accept a value of type univ. One of them always diverges, that's the second one. The other one takes this unique type, which is called beta here, this universal type beta, takes a unit value, embeds it into beta, and extracts it again, right? If univ only contains degenerate values, T1 is always going to diverge if we apply it to a value. T2 is also always going to diverge, that's obvious, right? So the two are contextually equivalent. Okay, so is this preserved? It turns out that in both of our settings, this degeneracy of univ is not preserved. Under a ceiling compiler, univ actually contains non-degenerate inhabitants. And how can you see this? You can sort of see you can choose this universal type X to be the untyped unit type of our untyped language, right? So you can just build this inhabitant of type univ with two identity functions, and that works, okay? That means that T1 and T2 are contextual equivalent in the source in system F, not after compilation. So contextual equivalence is not preserved. The ceiling compiler is not fully abstract. In the polymorphic Blame calculus, there is the same phenomenon. And instead of the untyped unit type, we take this gradual universal type, this gradual type star, and we can do exactly the same thing. So in both cases, the parametricity of system F is not exactly what's being enforced. So what can we do? How can we get back full abstraction? So let's look at a number of ideas, and actually none of these ideas are really what we want, right? So I don't see like an ideal solution to this problem. So I think maybe we're going to have to sort of adjust our expectations or something, or learn to live with this problem. Okay. So first, let's look at the polymorphic Blame calculus. If we really want to express the parametricity that we have in system F, I think we cannot really have a single universal type, a single gradual type in the polymorphic Blame calculus. What might work is this family of gradual types, where the gradual type is indexed with a set of type variables that are in scope, and where you can embed a value of a type variable alpha into this gradual type, if and only if the type variable is mentioned in this set of type variables that are in scope. How would this work precisely? I don't know, and this is something that maybe should be worked out, maybe not. I don't know how workable this proposal would be. I think this would be a way to restore fully abstract embedding of system F. Okay. Second, what about the Sumii Pierce compiler? So my intuition is that encryption is not enough to enforce parametricity. So pure encryption, and the reason is that it's really hard to avoid that encrypted strings behave as a kind of universal type, because we really want to be able to encrypt anything as an encrypted string, and we really want outsiders to not be able to look at an encrypted string and I mean, derive facts about what's inside. So how can we hope to prevent this existence of non-degenerate values of type univ? I don't see it, right? What I think you could do is to add primitives that go beyond pure encryption. For example, if we were able to look at a value and check that a certain seal is nowhere used, is not used anywhere in this value, that might be a way of then there might be a way of enforcing this non-degeneracy, this degeneracy of univ. But it's no longer encryption, right? It's no longer pure encryption, right? Maybe it's still useful, I think, because there are settings where such a primitive might be realistic. For example, if you have an adversary that's running on some kind of trusted hardware, like for the people who know that, capability machines with seals, where there's actually a runtime notion of seals. So maybe in such a setting that might be useful, but even then it's going to be a challenge to get this to be efficient, I think. Finally, if we're not able to fix these two things in a satisfactory way, I don't really like this indexing of the gradual type with with sets of parameters. It's useful to have a single gradual type, I think. I don't really see how you can fix the Sumii Pierce compiler. Maybe we should just modify the source language. So if we reduce the amount of contextual equivalences that we have in the source, then maybe we can build a fully abstract compiler with respect to this weaker contextual equivalence. So how could you do this? You could add a native inhabitant of univ. So in other words, you could add a gradual universe star. And does this break the nice properties that we have in system F? It does break some contextual equivalences, but not all. And in particular, you can interpret the results from ICFP'17 by Amal Ahmed about parametricity of the polymorphic Blaine calculus as saying that a language that embeds this gradual universe and system F still satisfies a form of parametricity. What our example shows is that this is not the same parametricity as the one that we have in system F. Okay, does this restore full abstraction? I suspect so, and it might be interesting to prove it, but I suspect this should work. So to conclude, these are sort of the results of this work. We disproved this 17-year-old conjecture by Sumii and Pierce. We propose this additional correctness criterion for gradual typing, that you have this fully abstract embedding of the typed language. We notice that the polymorphic Blaine calculus doesn't satisfy this proposed criterion. We also sort of point out that this ICFP'17 parametricity is different than the Reynolds system F parametricity, and then we discuss some perspectives. Okay, so thank you.
Thank you. So do we have some questions?
Hi.
Yes,
Yeah, I have two questions actually. The first one is, do you know if this also, I wasn't sure if I entirely got the counterexample, but do you know if this also applies to the non-parametricity paper where we use type-based sealing instead of term-based sealing? It looks to me like it does.
I suspect so, because so this non-parametric parametricity paper, that's where you have a kind of, sorry, there you have a kind of non-parametric notion of polymorphic functions. So you have functions that can inspect the type at which they're instantiated. And that means that if you have a type like for all x, you can make that sort of behave as a universal type, I think. So I haven't worked out the details, but I suspect that it applies there too.
Okay, my second question is, so it seems like you left out one possible observation at the end, which is maybe full abstraction is the wrong thing to be proving.
Maybe.
Is that thoughts?
I still think it's nice. I mean, so full abstraction is I think it's an intuitively desirable property. I mean, we want contextual reasoning, contextual equivalences from the source language. We want as programmers. So as programmers, we want to be able to reason in our source language, and we would like those equivalences that are the results of that reasoning to still hold after compilation. So.
Sure, I just mean like this counterexample, it's not clear to me why one necessarily cares about this equivalence holding as opposed to, I don't know. Do you have any ideas of some more useful equivalences that would not be preserved? Not that I have a characterization of what is not useful about this one. I'm just.
Well, yeah, I mean, even if you, I mean, you can say that some equivalences are maybe not stuff that we want to preserve, but even then, I mean, we really would like to know which of them are preserved, and to check that the ones we care about actually fall into the subset that is preserved. Yes, okay. Thank you.
So you mentioned one possibility could be to add a sort of universal type back into your source language, but then how would your source language be different from the target sort of gradual language?
Well, yeah, so I think you can do without some of the more fancy features of a polymorphic Blaine calculus, but you're right that it gets very close to the polymorphic Blaine calculus, yeah. Right. So it's just, I mean, I just see it as a way of relaxing the contextual congruence.